from the tiny gears in a watch to the massive bearings in a wind turbine. Anytime two things touch and try to move past each other, friction is there. Sometimes it's a pain, but sometimes it's absolutely essential. So, let's get into it.
Okay, to kick things off, let's start with a question you've probably experienced yourself. You've got a heavy box, right? Getting it to budge, that first push, takes a ton of effort. But once it's sliding, it feels, well, a little easier to keep it going. Why is that? The answer to that simple question really gets to the heart of what friction is all about.
You see, the whole secret behind that heavy box problem is that friction isn't just one simple thing.
Nope.
It actually has two different faces, two different personalities, and it all depends on whether something is standing still or if it's already on the move.
And here they are. First up, you've got static friction. This is the force you're fighting when you first try to push that box. Think of it like a stubborn guard that just digs its heels in. It actually matches your push, getting stronger as you push harder, but only up to a certain point. Once you break past that limit, kinetic friction takes over. This is the friction that's there while the box is sliding. And here's the key. Kinetic friction is lower than that maximum static friction. And that's it. That's why it's easier to keep the box moving.
Okay, so that explains what's happening, but it doesn't really explain why. Why is it so much harder to get things started? To figure that out, we have to zoom in. I mean, way, way in, to see what's actually going on between those two surfaces.
Yeah, the real reason for all of this is hidden from our eyes. It's happening on surfaces that we might think are perfectly glass smooth, but they're not even close.
Say hello to the asperities. That's the fancy word for these microscopic mountains and valleys that cover literally every surface. So when you put that box on the floor, it's not really sitting flat. It's actually resting on the tippy tops of millions of these tiny peaks. It's like two mountain ranges grinding against each other.
And these asperosities cause friction in two main ways. The first one is pretty intuitive: mechanical interlocking. The little peaks literally crash into each other and have to be broken off or deformed for things to slide. But the second one is even cooler: intermolecular bonds. At those tiny points of contact, the atoms from the box and the floor get so close that they form temporary bonds, like a kind of microscopic superglue. And to get the box moving, you have to break all those little bonds. This is also the reason static friction is higher. When the box is just sitting there, those bonds have more time to form and get stronger.
All right, so that's the tiny microscopic world. Now let's zoom back out and look at the big predictable rules that engineers use to deal with friction every single day. These are basically the fundamental laws of dry friction.
And it all kind of boils down to this really simple-looking but incredibly powerful equation. The friction force, which is F, equals the normal force, N, times this little Greek letter mu. And that mu is what we call the coefficient of friction. Okay, so what does all that actually mean?
Well, the most important part of that equation is the N, the normal force. And that's just a fancy way of saying how hard the two surfaces are being pushed together. For a box on the floor, it's just its weight. If you stand on top of the box, you've increased the normal force. And guess what? You get more friction. It's that direct.
Okay, so this leads us to a classic brain teaser that really trips a lot of people up. Imagine you have two blocks. They're made of the same stuff, they have the exact same weight, but one is wide and flat, and the other one is tall and skinny. Which one has more friction? Your gut probably says the wide one, right? I mean, more surface area touching the ground has to mean more friction, or does it?
Nope, the friction is exactly the same. I know it feels wrong, but for most solid objects, the amount of surface area touching down makes almost no difference to the friction force. It's one of the most counterintuitive things about friction, but when you think back to those little asperities, it actually makes perfect sense.
And here's why. You have to think about two different kinds of area. There's the apparent area, the big flat bottom of the block that you can see, but then there's the real area of contact, which is just the tiny, tiny sum of all those little asperity tips that are actually touching. With the wide block, the same weight is just spread out over more of those peaks. The pressure on each one is lower, but the grand total of the area that's really in contact ends up being the same. So same normal force, same real contact area, same friction. Wild, right?
So far, we've kind of been treating friction like the bad guy. And in a lot of machines, like an engine, it is. It creates heat, it wastes energy, it causes parts to wear out. So how do engineers fight back? Well, their number one weapon is lubrication. And just look at the difference it makes. That coefficient of friction, the mu we were talking about, for dry steel on steel, it's around 0.5.
But you add a thin film of oil, and that number plummets down to 0.1 or even less. You've just made those surfaces 5 times slipperier. That's a huge deal.
Now, lubrication isn't just an on or off switch. It actually happens in stages. At really low speeds, you get what's called boundary lubrication, where some of those microscopic mountain peaks are still poking through and touching. As things speed up, more fluid gets pulled into the gap, creating mixed lubrication and separating more of the surfaces. And finally, if you're going fast enough, you hit the holy grail, hydrodynamic lubrication. This is where a thick film of fluid completely separates the two surfaces. They aren't even touching anymore. They're basically surfing on a layer of oil.
But of course, getting rid of friction is only half the story. Sometimes friction isn't the villain, it's the absolute hero of the story. There are tons of situations where engineers are trying to get as much friction as they possibly can.
I mean, just think about it for a second. The static friction between your tires and the road is the only reason you can accelerate or brake or even turn a corner. Your car's brakes? They're just a really efficient system for using friction to turn motion into heat. Even a simple nut and bolt, it's not the bolt itself that holds things together, it's the immense friction created by the clamping force of that bolt. Without friction, our entire world would literally fall apart.
And it gets even cooler than that. Beyond just providing grip, friction can be used to multiply force in some truly mind-blowing ways. Let me show you one of the most elegant examples of this.
This is called the capstan effect. If you just wrap a rope around a post, the friction between them helps you hold on tight. And with just one single wrap, a pull of 100 newtons, which is about the force it takes to hold a 22-pound object, can hold back a load of 350 newtons. That's a 3.5 times amplification of your strength just from a little bit of friction.
But here's where your jaw hits the floor. The effect is exponential. Add just one more turn of the rope, and that same 100-newton pull can now hold back over 2,000 newtons. That's more than 450 pounds. You could hold up 3 of your friends with one hand. It's incredible. This is the exact principle sailors use to control gigantic ships with just a few wraps of rope.
So, as we've seen, friction is this amazing two-sided force. We spend so much energy fighting it, lubricating it, trying to make things more efficient, and yet at the same time, we couldn't walk or drive or build a single thing without it. So that brings us to the big question. What do you think? Is friction just some annoying bug in the physics of our universe that we have to engineer around? Or is it one of the most essential and useful features of our entire world?